Going live. We are going live. That's what my screen is showing me. And we will do a couple of problems. So this is day 2, LeetCode and Fluke. Day 2, we have an easy problem, the medium level. Let's start with an easy one, and I am doing a little bit of cheating. This is, well, sort of, yeah. I'm using a problem that I already solved previously. Just to make it easier, to start small. But the medium problem I haven't seen before, so I don't even know exactly what the topic of it is. So this is an easy problem. I hope you can see the screen. And the screen is being recorded, I hope. So it's one of the first 1,000. It's one of those interesting problems. Sometimes they're not really interview format. This one, so this one is add digits. Given an integer num, repeatedly add all its digits until the result has only one digit and return it. For example, number 38 has digit 3 and 8. If we add these digits, it will be 11. Then 11 has 2 digits, 1 and 1. If we add 1 and 1, it will be 2. Since 2 has only one digit, return it. And that kind of the problem. And there is a follow-up. Could you do it without any loop recursion in constant runtime? So I'm not sure I've done this iteratively, because I think I was interested in this constant time solution immediately. Maybe some next day I'll do it iteratively, but here it uses this number theory. The solution that's with constant time, that has the constant time solution is based on a number theory. Yeah, we all know number theory, right? So the trick here is, it turns out for this numeric system, for the base 10, there is a trick if you divide it by 9. So it turns out that if a number has digits that sum up to 9, then the result of this iteration of this of adding its digits will always end up to 9. And I think there is an exception, but almost always. Almost always. Or maybe there isn't an exception. I'm trying to remember that solution. So that's why I decided to kind of warm up on this problem, because I don't exactly remember all the details. I remember there are 3 cases, and one of them is this. So if you have 9, it has the sum of its digit is 9. Okay, the next, if you have 18, the sum of its digits is 9. If you have 27, so you look 9, 18, I'm going over products of 9. And we can go even to 99 and check out 99. So 27 still again gives you 9, but 99 gives you 18, and we know that 18 gives us 9. So, and even if it's 999, 999, what will that give us? 999. That will give us 27, as we already know. So here is the hack. If num is divisible by 9, evenly divisible, divisible by 9, then the answer is always 9. Return 9, right? Right, because 18, 27, 90, 99, they're all divisible by 9. There is one exception here, I think. And you can guess that if it's a 0, it will still be divisible by 9. If num is 0, if we divide it by 9, it will be 0. So the remainder is 0. The remainder of 9, I mean, you can divide it on 0. You can divide 0 on any number, you'll still get a 0. So we need to return. That's an edge case. We need to return 0. Now, so we looked at the 0 case, at the 9 case. What about the other cases? The 1, 2, 3, 4, 5, 6, 7, 8. Yeah, the 1 till 8. What about these? And that's another trick. It turns out that after we took care of 0, after we took care of that numbers that are divisible by 9, and if that number, not if that number, but the result is in all other cases, the answer is that number. The answer is that number divided by integer divided by 9, I think. Because if we have 10, divided by 9. The remainder is 1, and the 1 is the answer. So let's see, return num divided by 9. But what if it's 100? 100 divided by 9 will give us, yeah, the remainder will be what? Well, we know that, so 10 is 1. 11, if it's 18. Okay, so what's the remainder? Because yeah, I have a brain freeze. I forgot what remainder means. So the remainder means, okay, how many full 9s we have in that 100, which is, surprise, surprise, which is 11 by 9 is 99. And I mean, an easier case would be 91. So it doesn't matter if it's 91 or it's 901 or it's whatever, 9,000,000,001. All those 9s that are full, so evenly divided, yeah, if we divide 90 by 9, we'll have 10 9s plus 1. So yeah, though we only care about that one. So, and as we know, if we add 9 plus 1 will be 10, and 10 is as the sum of digit 1. So what I'm coming to is that we're looking at the remainder of, yeah. So the most general case, it turns out, is this case, the remainder of division by 9. And there is a couple of special cases. If it's evenly divided by 9, then then the answer is 9, not 0. So because 90 would give you the remainder 0, but it's 9 instead of 0. And if it's a 0, the answer is 0. And we run the code, and we get our answer. Yeah. So that's the solution. And we'll get to the next is the medium level problem. We'll get to it in a minute. We'll get to it in a minute. Stream, I wonder how stream works when you... So, are we sharing? Are we sharing? Find the student, share. Stop sharing, stop sharing. Yeah, I'm not sure. So I'll restart sharing. Find students. So we did a little practice with the warmed up a little bit on this number theory problem. We have we are restarting the clock for this medium level problem. And I mean, medium level problems can be different. Some of them feel like medium level, some of them feel more like easy level, and some of them feel harder than medium level. So let's start first. Let's try to understand it first. Find the student that will replace the chalk. Okay, there are n students, class numbered. Okay, so that's class students numbered. N students. The teacher will give each student a problem starting with the student 0. A problem, okay. And the student number 1, and so on until the teacher teaches the student number n minus 1. After that, the teacher will restart the process starting with the student 0. We'll give a problem starting. Okay, you're given integer array chalk and an integer k. There are initially k pieces of chalk and an integer k. Okay, so k pieces of chalk. When the student I is given a problem to solve, they will use chalk I pieces of chalk to solve the problem. However, if the current number of chalk pieces is strictly less, then the student number I will be asked to replace the chalk. Is strictly less than chalk I, then the student I will be asked to replace the chalk. Return index of the student that will replace the chalk pieces. Okay, let's look at the example. Chalk 515 A22. The students go in turn as follows. Student 1 uses 5, so it's 17. Student 0, student 1 is 1, 16 minus 5, it's 11, minus 6 minus 5 is 5. 2 uses 5. Chalk is 0. 2. So then the next one, student 0 doesn't have enough chalk, so they will have to replace it. Yeah, because student 2 was fine. It used all the chalk. It had enough. They had. Student, yeah, they had enough. Chalk. Okay, example 2. 25 chalk, pieces of chalk. Okay, so it goes. Number 0 uses 3. Number 0 uses 3 chunks. So, okay. Okay, so it was 5. Number 3. Student number 3 uses 2. K was 7. K becomes, minus 2 becomes 5. Minus 3 becomes 2. Minus 3 becomes 2. And student number 1 doesn't have enough chalk because they need 4 and they have 2. Okay, so constraints. There is n is up to 10 to 5 from 1. There is at least one student. Right? N is the number of students. And there is, the chalk could be at 1 or again 10 to 5, and K is 10 from 1 to 10 to 9. I mean, it sounds it sounds like a simulation approach. It will be just easy and straightforward here. Iterative. An iterative approach. Because what will happen, we have this 22, first case. Yeah, we take the first case as an example. Take the first example. The entire class has full speed of 11. 5 plus 5 plus 1. So I'm thinking of another approach that's going to be not as non-iterative. So probably I don't know if there is much value in it though. Well, it's you will still have to go over the n over n, but you'll have to go over n. But you will not hit this. So worst case, when k is 10 billion or a billion, right? 10 to the power of 9. What is 10 to the power of 9? It's like 10 to the power of 1 is 10. Yeah, so to the power of 9, it's a billion. And that's the worst case when we have a billion of chalk pieces to work through. And hey, good. How are you guys? Thank you, sir. So, Yeah, and if, let's say, if each student just uses one piece, and that will be a Boolean operations. We could run out of time with the Boolean operations. It could be quite lengthy. The simulation. So a more optimized approach will be to say, okay, can we use some math? Let's say 11, and if we divide the remainder divide by 11, so that will be 0. That means we don't have to iterate over that these students. We know that they will do 2 full rounds, or some kind of number of 2 full rounds, after which there will be 0 chalk, and we'll start from student 0, which is what it is here, from the first student. Again, now in the second case, it's 25, which is 25. Which is 25. And the sum total. Now let's call it total is 10, right? 3, 7, 10. Yeah, so what will happen after we do a couple of rounds, there will be 5 remaining, and after all the rounds, there will be 5 remaining, and then we can do the simulation, for example. Then we could do the simulation. And just go over the 3. We'll iterate over this list and go until it's not enough, and return that. So that should be quicker. That should be quicker. We remove all this what do you call them? Predictable consumption of chalk. Yeah. This predictable consumption, which is not going to give us the answer, but we'll need some iteration, lots of iterations. So it looks pretty, it looks, so we'll need to do. So we'll call it class I don't know, full class chalk. What to call it? Chalk. Class chalk. Spanned. Let's call it like that. Start with 0. Spanning consumption, spanning. Yeah, for this class, it's class chalk needs or class chalk, yeah, consumption. Let's just call it like that. It's fine. So we'll go over, yeah, so let's try to implement this solution. We'll go over the chalk range chalk and get that number. Then we'll remove all the redundant we'll say that k is k remainder divided by class chalk consumption. And by the way, if that class chalk consumption is smaller than k, let's say it's already 5 in this case. If we still try to divide, we'll still get a remainder of 5. So it takes care of that case as well. It takes care of that case. I mean, we could take care of that case quicker. We could do a check here if that thing is bigger than k already. So the moment it gets bigger, that means that that student needed more, so we can actually return I. But that takes care only of the case where it's bigger, okay? Now, where k is initially smaller. But when it's not smaller, we need to do this dry run. Hey, dry run, and then basically do the same thing. What it means the same thing? Well, it's sort of the same, but it's class chalk. So we now have the remainder of k, and we need to know where in range, how to spell range, where in that process you will have okay, I'm getting a little distracted. Yeah, where we will actually have So we'll do the opposite. We'll go k is minus ek. So and if k is less than 0, we return b. What if I think we just need a simple return of anything here. Range chalk iv. Oh, return I. Oops. So let's see. Yay, it worked. And what I like about it is it's not the fastest though, but it's quite fast. So let's see. I mean, we can probably remove that check. And oh yeah, we don't need that then. And get, so it's a little bit slower, but I mean, it's pretty much the same. It makes sense to do this check, yes. Oops. I wonder, well, so yeah, solved, basically. Solved in 20 minutes. And this problem feels more like, I would say, on the easier side. I'm not sure if it's if it actually medium. It doesn't really feel medium by complexity, but yeah, let's still give us the credit we deserve. Is there any is there any way to just refactor the code to make it short? I don't know, like shorter, or maybe do have one loop instead of two? One loop instead of two, because we need to know that before we can do this calculation, get that remainder, and yeah, I'll think about it. But as for a working solution, that's it. Yeah, I'm not seeing right now if we could do that. If we could do it with like in one loop or some other optimization, it's not going to really change the time complexity, because this is a big O N time complexity. Could there be a math-based solution here with like fixed time, constant time? No, you still need to go over the loop, over the the data, at least one the chalk array, at least once. And we do it here once, and then we do it here just another time, one more time. But I mean, to do it all in one loop. Because yeah, we need to know that number, as I mentioned already. Only then we can tell. We can do this. Yeah, let's call it a good working solution, because it looks like it is. I mean, optimized enough. So yeah, it looks like that will do. 43 minutes with discussion, with a little bit of discussion. That's our stream. Thank you for watching. Like and subscribe. See you in the next video.